I wonder who here has ever heard of polymorphisms? Sure. Okay. Yeah. So we're going to start with some definitions just to tell you what polymorphisms are. So let's start with this specific case. So a function f from 0, 1 to the n to 0, 1 is a polymorphism of binary XOR. Okay, so I think of binary XOR as a function from 2 bits to 1. If for all x and y, f of x, XOR y, is equal to f of x, XOR f of y. Okay, where I extend XOR from bits to vectors in the natural way. Okay? So a function f is a polymorphism of XOR if it satisfies this equation for all x and y. Okay, so which functions are polymorphisms of XOR? It's not a trick question, no.
Coordinates.
Okay, so yeah, we're interested in this talk about characterizing polymorphisms and then approximate polymorphisms of arbitrary functions. But we're starting with a case which might be familiar to some of us who do this sort of thing.
Dictatorship, what you're talking about.
Okay, so dictatorship, that's one example, but there are also other examples. Okay, now do you think of any other example? Just so we get the definition straight. Okay, so maybe we start with this example that Gilad gave. So if you take f of x is equal to x 7, then f of x XOR y is x XOR y 7, which is the same as f of x XOR f of y. Okay, well, maybe there are other examples. Constants. Constants, right? So f x equals 0 works. 1, I think, doesn't work. But the concept 0 works. Any other examples?
Any linear function?
Any linear function, yeah. So here's the theorem. I'm not going to prove, but it's an exercise. Let's say it's a folklore theorem. The polymorphisms of XOR are the functions so you go over some set S and you XOR all the coordinates in that set S. So it's really parity. Okay, and this is because XOR is associated, I guess, commutative associated. Okay? So that's just to get the definitions straight. Yes?
Why is it 0, 1 valued?
XOR? So
there you wrote it as a polymorphism. Oh, okay, and only the function 0, 1 valued.
yeah, so
the thing itself takes values in R or something.
no. So if you take an XOR of several coordinates, you still get 1 bit. So each of the XOR are bits.
Okay.
And I'm just taking a parity of a subset of the coordinates.
Okay.
Okay, and you can show it's not very hard that these are the only solutions, and you can check that all of these are actually solutions. Okay, so hopefully now we know we understand the definition of polymorphism. So maybe let's take another example. Okay, so you can extend this definition where reflecting this XOR by any other function. Okay, so we'll give an example. So f is a polymorphism of the majority function on 3 coordinates if for all x, y, and z f of majority x, y, and z is equal to the majority of f of x, f of y, f of z. Okay, where you define majority of x, y, z, it's the same way, just doing it coordinate by coordinate. Okay, so what are the polymorphisms of majority? It's not something you're supposed to know, but let's see some examples. Let's start with the examples we had before. Okay, so x7 still works. Yeah, so if you just meant to replace f by the 7th coordinate, then you'll get the majority of x7, y7, z7, z7, and here you'll get the same thing.
Everything works. Doesn't everything work?
No, for example, if you take majority, I don't think it's going to work. Yeah, covering would be harder to do. But, yeah, so here are some examples. x7. We have the Sasha's suggestions constants, so 0, 1. You can also do 1 minus x13. It's not 1, 3, it's 13. Okay, this also works. And so we call these trivial polymorphisms. Okay, so functions like x7 are polymorphisms of every function. Okay, no matter what I replace the majority with, it will always work, these kinds of projections. These anti-projections, they will work if your function is odd, like majority. And the constants will work, well, if when you substitute zeros, you get 0, and you substitute 1s, you get 1.
I don't understand.
Yeah.
There is a function on the cube. And what does an f of majority? Majority is a number, 0 or 1.
So you can apply to each coordinate.
Yeah, so you extend majority from bits to vectors by applying it coordinate-wise.
Oh, you mean applying entry-wise?
Entry-wise, yeah. So maybe x is 0, 1, y is 1, 1, and z is 1, 0. So the majority is going to be 1, 1. Okay, this is how I extend it to vectors. Yes, I'm going slowly on purpose so we know what we're talking about, because otherwise you will be completely lost and it will be pointless. Okay, so please ask questions. Okay? So this is how I extend the definition of my given small function, which I usually will call g, from bits to vectors by just doing it coordinate-wise. And then these trivial polymorphisms are always polymorphisms. I mean, there are some constraints, but these are like the boring polymorphisms. And the question that is interesting from, okay, so this comes up in several different areas. So it comes up in universal algebra, whatever that is, and also in social choice theory. And in social choice theory, they would like there to be some interesting polymorphisms. Okay, but in this case, there are no interesting polymorphisms. These are the only polymorphisms. Okay, you're not supposed to see that, and I'm not going to prove it. You just have to trust me. Yeah.
Could you say a bit more about why they want interesting polymorphisms?
Let's take as an example Arrow's theorem. So it's a slightly different thing because we're looking at polymorphisms of predicates. Okay, so just if you haven't seen my talks from a few weeks ago, then just black out for a few seconds. So there, at Arrow's theorem, they think of it as an impossibility theorem because you only have the trivial ways of. So they call it a domain. A domain for them is a predicate, an impossibility domain if you don't only have trivial polymorphisms. Yeah. Now you can tune back in. So you weren't supposed to understand that, and now you can tune back in. Yeah. So now I'll tell you what all the polymorphisms of all functions are. It's not so hard. I'm not good, but it's well-known result. No one will be able to post, probably maybe even earlier. So solve this problem for predicates, which is something I might get to in the end. And this is this special case is even easier. So suppose G is a function from 0, 1 to the n to 0, 1. So this is going to play the role of binary XOR and a majority of 3 coordinates. And suppose it depends on at least 2 coordinates. Okay, this is just to rule out the trivial cases. If F is a non-trivial polymorphism of F, then one of the following holds. So either
If G is a non-trivial.
right, right. Okay. Although you can ask it whether a function is a polymorphism itself. It will be the same answer. Yeah. Then one of the following holds. Okay, so either F and G are possibly negated XORs, or F and G are AND, or F and G are ORs. Okay, in all these cases, it's not necessarily 2 coordinates, it can be any number of coordinates. Okay, and what we're using here is that XOR, AND, and OR, they're all commutative and associative, so we will be able to do this rearranging that worked in the case of binary XOR. Okay, so really, there's a different way to state this result because it's symmetric in the 2 functions f and g. Yeah, so it's really either f is trivial or g is trivial or one of these cases. Okay, so like the only reason that this funny condition holds is due to these kinds of rearrangements. Like if the source of it all, there is this binary operation, which is commutative and associative, and over 0, 1, these are the only options. And you can also ask this over higher alphabets, but then it gets a lot more complicated. Okay, we're not going to prove this result, just background. Yeah.
So what are XORs, ANDs, and ORs?
Yeah, so let's take an example. So f of x is equal to x10, xor x13, and xor x5. This is an example of an XOR. It could be negated, potentially. And if you replace XOR by this is an AND, and this would be an OR.
Maybe there's also the question is define XOR, I'm not sure. Define the symbol.
Oh, okay. So yeah, A XOR B is just A plus B mod 2. Or you can think of A and B living in the field with 2 elements and you just sum them. Yeah, it's exclusive OR. Yeah, sorry, I used to talk to computer scientists and okay, so we think we understand this result. Okay, I think the usual proofs are by induction. I'm not sure. We have a Fourier proof of this, but we can prove it in many ways. Okay, but so I'm coming from a Boolean function analysis background, and in this field we usually don't like statements which have a for all in them. Right? Usually in the setup there is some probability measure, and there is some probability that something is happening. Okay, and this is why we're talking here about approximate polymorphisms. Okay, so what's an approximate polymorphism? So again, we take the example of XOR. So F is an approximate polymorphism of, rather an epsilon approximate polymorphism of XOR if the probability, when you take X and Y at random, as f of x XOR y is equal to f of x epsilon f of y is at least 1 minus epsilon. Okay, so now I'm not tricky. It's okay if for a few x and y's then this fails to hold. And the question is, do I get anything new? Yeah, so in this errors example, is now I don't want the function to work always, just for with 99%. And I now go around this impossibility theorem. Okay, and here there's a very famous result in our community. So I think we don't have that many representatives from this community, but some of us know this. So how do you call this result which classifies all the approximate polymorphisms of X over? It's a trick question, so people who actually know the answer should answer.
Sorry, I missed the question.
So how do you call this result that classifies all the approximate polymorphisms of X over?
Robustness of linearity testing?
We'll just call it linearity testing, okay? So there's this famous result which is features in complexity theory and property testing, PCP, whatever these things mean. Okay, but it's easy to state and to prove. So any epsilon approximate polymorphism of XOR is epsilon close to a polymorphism, to an exact polymorphism of XOR. Okay, so the only way in which you can satisfy this probability 99% is if you're 1% close to an actual XOR. Okay, so my notion of distance is just that the two functions differ on an epsilon fraction of inputs. Okay, this is proved using a very, very simple Fourier calculation, using the fact that the characters are characters. Yeah.
When this result?
Do you remember?
88, if I remember correctly, by Bloom, Luby, and Wilfold, and they didn't use Fourier.
Right.
Fourier came a little bit later.
There is a much older result called Boolean stability. So I'm not sure. I mean, just for historical purposes.
No, I mean, it won't be surprising if it's even earlier, because it's such a...
Yeah.
How is it called?
Boolean stability.
Yeah, we'll look it up.
Yes,
Yeah, so we know it, this thing has two proofs in our community. One of them is this Fourier analytic, and the other one uses, how do you describe it, like local decoding?
Correction procedures. They
Self-correction.
show how to correct the function without changing too many values and get a purely additive function.
Yeah, it uses something known as the magic square. If you're interested, you look it up. It's very nice, and it also extends to other tensor codes, product codes, or something.
Yeah, both methods have their applications. You can also randomize this. Those computer scientists extracted a lot from these things.
Okay, so now you can probably guess what is going to be the main theorem in this talk. So, anybody wants to guess while I erase the board? Go ahead, I'm sure all of you can
The
guess.
epsilon approximate of any T is epsilon.
Yeah. Unfortunately, it's not true. It's almost true. Okay, so yeah, so we ask now, give me a sum function g, what are the epsilon approximate polymorphisms of g? And you would expect the answer to be that it's close to an exact polymorphism of g, and this is almost correct. So sometimes you can criticize these theorems as, yeah, we knew the answer, so now you're just giving us the proof, who cares about the proof, you know. But no, something actually somewhat surprising happens, and you discover it when you do the proof. So there is some kind of point in doing the proof. Yeah. So just to simplify notation, I think I will use ternary predicates, but it works in general. So if, I guess in this statement it won't make a difference. if f is n rather, so for all epsilon there exists delta such that if f is an delta approximate polymorphism of G, and G will be ternary, just so I can write an equation. Then F is epsilon close with respect to mu half to, this is just a uniform distribution, maybe it's hard to read, to a function f, some function f, and epsilon close with respect to mu station of G. So this is some bias measure where you get one's probability which corresponds to the output of G to some h, such that, hope I get it right, h of G of x, y, z is equal to G of f of x, f of y, f of z. Okay? So we're looking at a slightly larger class of equations. Okay, so previously this f and this h were the same thing, but now we need to look at this what we call a skew polymorphism, a slightly different version. Okay, now if G happens to be balanced, then f is going to be equal to h. But if not, then it's not necessarily the case. So now what I'm going to do is I'm going to give you first an explanation why this happens, and second I'm going to give you all the new examples that we get. Okay, so why did this happen? Because you can define f in the following way. So it's going to act like f of x if x over n is roughly half, and like h of x if x over n is roughly the expected value of G. Okay, so basically f can tell whether it's on the right-hand side of the equation or on the left-hand side of the equation just by looking at the statistics of its input. And that's why it's really two functions in one. And you have to do this thing to see what's going on. Okay? So, stated differently, if I give you functions capital F and capital H which satisfy this equation, then I can construct a single function little f which contains both of them, and it's going to satisfy the original equation with probability very close to 1. Because it can tell whether it's on the right-hand side or on the left-hand side, just looking at the statistics of the input. Okay, there will be some little of 1 error. Yeah, so if the input is like balanced, then probably you're on the right-hand side, and if it looks biased to the output of G, then probably on the left-hand side, and otherwise we don't care because it never happens. Yeah, so you can fill the blanks in any way you want. Yeah, of course, it only works if G is not balanced. If the G is half-half, then it won't work. Okay, so do we actually get anything new? So you can take G, which is G of ABC, which is A or B or C complement, which is also A complement and B complement and C complement. And then I think we want to take F is going to be an OR and H is going to be an N. I always get this thing wrong. Yeah, so we won't do the calculation, but if you open things up, then, and I didn't mess up the order of F and H, then this would work out. Okay, so you have this De Morgan's law, and somehow it works in our favor. And you can also do it opposite, with and instead of or. Okay, so this is the new solutions that you get. And actually, when Dahl gave the first version of this talk, then somehow we forgot that we had this case, and he gave the theorem like without this case. So he presented the wrong version of the result, although the proof was correct. So this also happens sometimes. Okay, so any questions about the statement of the theorem? Who is completely lost? Don't be shy.
Is it reasonable to formulate a version for continuous spaces?
For continuous spaces, yeah, I mean, you can think of functions like or and like maximum and minimum, and you can probably do it. So. Yeah, but this would be quite different. Yeah, so for particular gadgets, G, you might get particular proofs, which are easier. Imagine in the continuous setting, like your function will have to be nice enough, so you can say something. Yeah, but we don't even know how to do it for larger alphabets.
Where you said you do or you don't?
We don't. There are some issues.
And the reformulation was that if you have G, big F, and big H, which satisfy this, then you can define just little f. Okay.
Yeah, I mean, it's probably true, but there are some issues. We'll get into them soon. Yeah, any other questions? Okay, so now the ambitious plan for the remainder of my time is to give you, describe to you a proof of this theorem. Okay, and if there's still time, then I'll discuss some open questions, but probably this won't happen. Okay, so there's like a history around this work where we first handled the and predicate. So this was also together with Nitin. Elchanan had some idea, and we worked it out. But this was only for that particular predicate, and then we came up with this argument, which is more general, but gives worse parameters. And actually, if you for some reason wanted to take a look at the paper, then you can see there are also some other parts which I'm probably not going to cover because it would be too much. So really the reason I'm giving my talk is because of the technique, which Dahl said it might be useful for something else. So hopefully I'll get to it, and then you can say if it's useful for anything else. Yeah, so the plan of the proof, it's in 2 steps. Okay, so step 1, yeah, we're proving this theorem. Step 1, show that f is close to a junta. Okay, a junta is a function that depends on few coordinates. Okay, so we somehow show that f is close to a junta. Yeah, so it secretly depends on a few coordinates, or it's at least close to. Yeah, you can see this is already something is fishy here, so if anybody notices, let me know, otherwise I'll spoil it for you. And step 2 is finish the proof. Finish the proof. And I don't want to spoil, but there is something nice is going to happen. And we're going to start with the second step. Okay? Just because this was also our starting point. So I first came up with this idea of having the second step, and then the real work is in the first step. Okay? So suppose that, in the first step we're going to prove the following lemma. So for all epsilon there exists an eta. This is supposed to be an eta. such that if F is an eta approximate polymorphism of G, then F is epsilon close to J junta F. So this just means that it's a function which depends on J coordinates. Okay?
The polynomial, polymorphism, okay.
Yeah, sorry, the polymorphism. Okay?
And that's always a uniform measure?
Yeah, so you can do it with respect to any bias measure with constant bias, but it will just be exactly the same, so it's pointless. You know, but if you really care about this,
If G is a XOR, the first example,
excellent, yeah.
how can, it's not going to
Right.
hold?
So the actual term of the proof is, yeah, if G is an XOR, then we already know how to prove it, and otherwise we do this. Yeah. So good catch. Yeah. And we'll see how it comes, where it comes in. We'll come in at a particular spot. Hopefully we'll get there. Yeah. Okay. So we write this equation. Well, the equation that we started with, f of g of, and we're going to separate it into two parts. Yeah, let's do it like this. So I'm separating each of the coordinates into the primes, which are the junta coordinates, and the double primes, which are the noise coordinates. Okay? So it will look like this. Okay, so we know that this holds with probability 1 minus delta, where we can choose delta. Okay, so this is the assumption. And we also know that F is close to this capital F, which is a junta. Okay? Now, we can fix the non-junta coordinates, the noisy coordinates, so that all of the following happens. So we fixed x prime prime, y prime prime, z prime prime, such that so fx prime prime, is the function where I put the particular x prime prime in the noise coordinates. Okay, maybe we fixed it to less confusing. Okay, so these functions are close to f, and star holds probability 1 minus order delta. Yeah, so if for typical ways of fixing the remaining coordinates, then this little f is still going to be close to the junta, and this equation is still going to hold. Okay, and now we define
What is the capital F?
it's the junta that little f is close to.
Okay.
Yeah, we define W0 prime prime, which is g of x0 prime prime, y0 prime prime, z0 double prime. Okay? So now what I'm going to do is I'm going to replace f by all of these juntas. Actually, I don't even need to do this. So yeah, what we get is that f w0 prime prime g of x prime, y prime, z prime. This is equal to g of, I'm sorry about all of these double primes, but it's inevitable. Okay, so this happens with probability 1 minus order delta. Okay, so like for average fixing of these noise parts, then everything will still work on average, and now you apply Markov inequality, and you get that all of these things work with some constant factor lossing parameters. Okay, but this is just technical details. So if you take typical values of these noise parts, then still f is close to this capital F, and this still holds with good probability. Okay. And now the observation is like I can choose delta as small as I want. Okay, and now this equation, it only involves a few variables. It involves 3 capital J variables. So if this order delta is smaller than 2 to the minus 3j, then the equation always holds. Okay, so I choose this error parameter delta, which I can choose because I can choose it. So small that this promise is already going to guarantee that we get no errors at all. Okay, just because it involves very few coordinates.
Your J here doesn't depend on any parameter.
Right. So it only depends on epsilon. Okay, so I start with epsilon, I get eta and j, and then I choose delta. Yeah, so it's right that we have to worry about not being circular, but it's okay. Okay, so we removed all of these non-interesting variables, and now we're like essentially in a finite situation. And you can just choose the probability that this polymorphic equation is falsified to be so small that it's really 0. It's exactly 0. Okay? And now, because these f's are all close to capital F, then it's not like they describe only this particular fixing of the noise variables, they actually describe all of the function. Yeah, so what this means, so I can mentally replace these with a capital F and this with capital H, and then I'll get the statement there. Yeah, and I think I'm not hiding anything, almost. Okay, so the one thing that could go wrong is that it's true that these functions are close to capital F and so close to one another, but it's a different equation which involves different functions for every coordinate. Right, so it's not only F and H, we have Fx, Fy, and Fz. Okay, so it might be that there is some even more complicated solution, but it doesn't happen because we also know how to classify all of these solutions. Okay, so really you need to classify all the solutions to this kind of equation, but where all the capital F are different. Okay, and you do this and everything's fine.
You do that by hand, or?
Yeah, so I think it was known, but we also have a Fourier proof. It's probably I think it was known. It's like a response to multi-sorted universal algebra, or from a social choice perspective, you aggregate the opinions on every agenda item in a different way. It's like it's a natural thing. Okay, so this was the reduction to just showing that F is a junta. Okay, it's really a reduction to the 0 error case. Okay, so while I erase the board, you can think about if you have any questions, and then we're going to attempt to describe the interesting part of the proof, which might be possible. Yeah, so any questions? so now we do step 1. Okay? So step 1 is to prove this lemma. Okay? So we're given that f is an eta approximate polymorphism of G, and we want to show that f is a junta. And so we need to use the fact that it's not an XOR, because otherwise it's not true. And what we're going to use is there is some input with some insensitive coordinate. Okay, so I'll give an example with the majority. So for majority, so majority of 0, 0, 0 is equal to majority of 0, 0, 1. But the coordinate, this third coordinate is relevant. So there's some other input where it does make a difference. So majority of 0, 1, 0 is not the same as majority of 0, 1, 1. Okay? So we can always find this kind of input and this kind of coordinate unless it's parity. Okay? This doesn't work in larger alphabets. Okay? This is the point which doesn't work. Okay, so this is how we're going to use the fact that it's not parity. That G is not an XOR. Okay. Yeah, so we need to make f into a junta. So how do we do this? So if you've been here for my lecture series from a few weeks ago, then you take the variables with large influence or something like this. But no, we need to do something different. We use Jones regularity lemma. Okay? So you can decompose any function at all, into parts which are pseudorandom. Okay, so you can represent f, any function f, and particular our function f, as this kind of a decision tree. Okay, so this is a decision tree. Okay, and you get many leaves, and almost all of the leaves are pseudorandom.
Did you say Jones regularity lemma?
Yeah.
Chris Jones?
Yeah. I think Elchanan also knew how to do it, but I think it's never been published, but it's on archive. Yeah, so what I mean by this being pseudorandom is that if you restrict the variables along this branch, and now you get a new function on a slightly fewer coordinates, and this function has to be pseudorandom. Okay, in what sense? The low degree influences are small. If you don't know what this means, we don't care. Okay, so for some notion of pseudorandomness, it is going to be helpful for us. Okay, the way this thing is proved is if this function here is not pseudorandom, then there is some bad coordinate, and you branch on it, and you continue, and the proof is really easy. It's basically now you can, those of you who know what low degree influences are, you can reconstruct the proof. It's really simple. Okay?
You want some control on the depth?
Yeah, so we need, so if you specify how pseudorandom the leaf should be, and also what is the probability that the leaf is bad, then you should be able to bound the depth of the tree in terms of these parameters.
Only.
Yeah, only these parameters. That's not surprising, look, all the regularity lemmas are like this. Like every graph is pseudorandom. Yeah, I don't want to get too technical. Yeah, so let's ignore the issue of bad leaves. I mean, that's not a big issue. Okay, so let's assume that all of the leaves are pseudorandom. We want to say that this function is really a junta, which means that these functions are really constant. Okay, so it's going to be a proof by contradiction. So we assume that many leaves are far from constant and show that this equation doesn't hold fails with probability. I'm writing here omega 1, but there are some epsilons here. Some probability that doesn't depend on delta, which the delta is probability that it should fail. Okay, and then I choose delta small enough, and I get the contradiction. Okay. So this is the idea. And how do we do this? So we're going to consider two coupled inputs. Okay, so first we're going to choose a leaf at random. Many of the leaves will be good. Let's just say that we want to show that if a leaf is random, then it essentially has to, the function has to be constant. Okay, so here is the xy, so the x, y, and z, and we sample them at random, and I'm only describing the part which is at the leaf. So not the part which was fixed. So maybe it's like this. Okay. So we z and z prime. Okay.
This is the path of computation?
No, this is the function at the leaf.
Ah, this is just the values.
Yeah, so now it's inputs to the function. So now I'm looking at this equation, but now my f is the function at the leaf. Okay, so I'm going to show that if a leaf is not close to constant, then this will fail with some appreciable probability. And then I'm going to take some, say, yeah, if it happens for many leaves, then this will fail with some constant probability, so it can't happen. So I just need to understand what happens in a single leaf. Okay, so here's the inputs x, y, z to this f, which is really just a single leaf. So this is one input, x, y, and z, and now the coupled input, it will have the same x and y, but the way I do z prime is, if I see 0, 0, then I resample it. Okay, so this is resampled, and otherwise I copy it. Okay, so now I have two coupled inputs, and each of them individually has the correct distribution. Okay, now, why do I do this resampling in this way? So this resampling, it ensures that g of x, y, z is going to be equal to g of x, y, z prime. Okay, so if I, in particular, if I look at f of these things, then they will be equals. So to get that this equation fails, it's enough to arrange that g of f of x, f of y, f of z is different from g of f of x, f of y, f of z prime. Okay, and how can this happen? So now I look at this other input. So because my function f is far from constant, then there's some appreciable probability that if I apply f here, then I get 0. And there's some probability that if I apply f here, then I get 1. Okay, and now I want to say that because I'm resampling so many, like around 1/4 of the inputs, then there is some probability that what I get here and what I get here are different. Okay, and if I can show that all of these things happen with some appreciable probability, then I get this actually failed with some noticeable probability, and I get my contradiction. Okay? Now, the main issue here is that there is some dependence between my two events. So, yeah, let's say that my function is, for sake of contradiction, is epsilon far away from constant. Okay, so this will happen for probability epsilon squared, at least. And let's say that I showed that this happened with probability, I don't know, epsilon to the 10. So maybe the probability that both of these things happen is 0. Right? So this is like the punchline, which is why I'm giving this talk. This is this technique that Dole thought was interesting. So there's this result in Boolean function analysis called "It's ain't over till it's over." It's supposed to be the name of a song. Ain't over till it's over. You know this song? Possibly a myth. I'm sure Rocco knows this. Ain't over till it's over, or something like this.
It has to be like 80s.
Yeah. So it is this situation. So let's see how it looks from the point of view of z and z prime.
It's just an idiom, right? It's something that people say.
Yeah. So first I choose at random 3/4 of the coordinates and I fix them to some value. Okay, and after that I'm just, these are the fixed coordinates, and then the remaining coordinates I take two completely independent samples. So what I want is that after I do this random restriction, where I fix the values of 3/4 of the coordinates to random values, and after that, it's highly likely that my function, which was originally far from constant, is still far from constant. Okay, so it will be so likely that it beats this thing. So it's the probability that it's not far from constant should be smaller than epsilon squared. And what this theorem says is that if this function is pseudo-random enough, then it will happen. Okay, so, and yeah, if this function after this restriction still has some variance, then you'll get to a different value with some appreciable probability. Okay, so I'm out of time, so let me just repeat it once again and I'll finish. So again, we want two things to happen. The first thing we want to happen is that here we get 0 and here we get 1. Okay, and for all we know, this happens with some bounded from below probability, but not close to 1. And here what we want to happen is that we get two different values. And this also happens on its own with some small probability, but bounded away from 0. And we want to say that actually the probability that both of these things happen is also bounded away from 0, although they are dependent. So the trick is to deconstruct this event into two things, where the first one is highly likely. So the first one is that after you fix these coordinates which are the same, then still the function has variance. It's still not far from constant. And this will happen if your function was pseudo-random to begin with, in the sense that Jones' regularity lemma gives you.
And this is because it ain't over.
Right, so it ain't over till it's over. So you don't know the value of the function.
So this
Even
is
if
the
you
theorem.
yeah, even if you fix, so you started with a function which was kind of not constant, and you fix 3/4 of the coordinates to random values, and you still have no clue what the answer is going to be. With a high probability, it ain't over. Yeah, that's the content of this thing. Okay, so I guess I'm already over time, so it's a good place to stop.